Hi everyone, and thank you for attending today's webinar, Hello AI World, Meet Jetson Nano, hosted by Dustin Franklin. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets. All of the widgets, as well as the slide area, are resizable and movable, so feel free to move them around to get the most out of your desktop space. If you have any questions during the webinar, please submit them through the Q&A widget. We'll try to cover as many questions as possible during the Q&A portion, but if there's any we don't get to, please post them on the forum to keep the conversation going. Be sure to check out the resource list for links to the developer site, forums, wiki, and more. And if you run into any technical issues during the webinar, you can find answers to some common questions located in the Help widget at the bottom of your screen. An on-demand version of the webinar, as well as the slide deck, will be emailed to you later today. Before we get started, we wanted to do a quick poll to see how many of you have Jetson developer kits today. And if you have a dev kit, which one or ones do you have? Okay, let's get started. Here's Dustin.
Hey everyone, thanks for joining us today. We're excited to be with you to talk about Jetson Nano, how you can use it to create your own AI-powered projects, and to take your questions. We've got a packed agenda for you guys today. There's been a lot of excitement around the Nano, and we're going to be covering the details of the hardware, followed by its software stack and the supported machine learning frameworks that you can run on it. We have deep learning inference benchmarks to share, along with the latest updates to TensorRT, and we've recently released the Isaac Robotics SDK and simulator. We're going to dive into the array of resources at your disposal to get started with Nano, including our AI tutorials and a bunch of tips and tricks to help you along the way. At the end, we'll take as much QA from the audience as we can, so let's get started a while. For those of you who aren't familiar yet with Jetson, it's NVIDIA's family of embedded high-performance AI computers, often used to deploy deep learning and computer vision for autonomous robots and AI at the edge. Having the compute capabilities for AI at the edge gives platforms the ability to make intelligent decisions in real time out in the field, often in some very remote locations. On these platforms, there's lots of high-definition, high-frame-rate sensors needing processed with low latency. It takes a lot of compute horsepower and flexible software in a compact size and power-efficient package to achieve that. Many of today's most advanced autonomous robot platforms use Jetson for these reasons, with applications like last-mile delivery, warehouse logistics and inventory management, precision agriculture, industrial inspection, and pick-and-place in manufacturing. The market for these is growing incredibly fast now that the compute is available for AI out at the edge. And for the most compact, low-power applications, and for those who are looking to get started with AI, we have a new member of the Jetson family to introduce, Jetson Nano. Jetson Nano is our smallest, lowest power, and least expensive computer that NVIDIA has ever made. This is the Nano Developer Kit, and it's a complete embedded AI computer that has an NVIDIA GPU on board capable of 472 gigaflops of compute with full support for CUDA 10, a quad-core ARM 64-bit CPU, 4 gigs of RAM, and it's only $99. It's fully compatible with Linux and the NVIDIA AI platform, it's supported by NVIDIA software, and it has the performance and power efficiency to run modern AI workloads, all in 5 to 10 watts in a compact footprint. The $99 dev kit includes a Jetson Nano compute module, along with a reference carrier board that has 4 USB 3 ports, HDMI and DisplayPort, Gigabit Ethernet, M.2 with PCI Express, MIPI CSI camera connector, 40-pin GPIO header including I2C, SPIES, and UART, and a micro SD card slot. The camera flex cable connector is compatible with popular MIPI CSI cameras like the IMX219 based Raspberry Camera Module V2 and others that our imaging partners have created also. The 40-pin GPIO header on the dev kit is similar to the 40-pin header on the Raspberry Pi, which means you can use a lot of the same devices and accessories with it. There are 3 primary ways to power it, which we'll discuss in detail later, all of which use 5V DC. You can use a micro USB charger, the DC barrel jack adapter, which is capable of delivering more power if you have a lot of peripherals plugged into the board, or power over Ethernet. The Nano Dev Kit boots Linux from the removable micro SD card slot. The distribution of software for Jetson we call Jetpack, and the current distro is based on Ubuntu 18.04. The processor has an integrated 128-core NVIDIA Maxwell GPU, 64-bit quad-core ARM Cortex-A57 CPU, 4 GB of LPDDR4 memory, and 4K hardware video encoder and decoder, capable of simultaneously decoding 8 HD video streams and encoding 4 HD video streams at once. Jetson Nano is made for processing lots of high-definition sensors and multimedia with AI and analytics. You can get these developer kits from a variety of suppliers worldwide, including Arrow, Amazon, Newegg, Seed Studio, SparkFun, and Silicon Highway, and more regional distributors coming online soon. So I mentioned that the developer kit includes a Jetson Nano compute module and the reference carrier board. Jetson Nano is actually a 45 by 70 mm embedded module that can be integrated into production products and devices. The compute module contains all the processing, memory, and storage on board, and it provides all the I/O through its 260-pin SODIMM style edge connector. Embedded system designers can design their own carrier boards from the reference carrier board included with the dev kit that routes the I/O to the connections and ports that they desire. The Jetson Nano compute module has the same processing capability that the dev kit does. It's a 128-core GPU, quad-core CPU, and 4 GB of RAM with the same core clock frequencies and performance. To accommodate embedded use cases, it has different storage than the dev kit. It has a 16 GB eMMC instead of the dev kit's removable SD card. It also has an extended warranty, and the production module is going to be available shortly in June with volume pricing of $129. Here's a full list of the Nano module's I/O, which the dev kit's reference carrier board breaks out a subset of. There are 12 MIPI CSI2 lanes, which can be used to stream up to 3 4-lane MIPI cameras simultaneously, or 4 MIPI cameras in X4, X2 configurations. And more cameras can be connected over USB, Gigabit Ethernet, or PCIe. There are 4 lanes of PCIe Gen 2 to use, with one controller that can run in X4, X2, or X1 mode. If you want to attach multiple PCIe devices, you'll want to use a small PCIe switch on your carrier to bifurcate the lanes. As mentioned, the production module has 16 GB of onboard eMMC storage as opposed to the dev kit's removable SD card slot. There are more GPIO available on the module and more I2C, SPI, and UART buses, in addition to embedded DisplayPort and MIPI DSI display interfaces. In June, we'll be releasing the hardware docs and design guides for the module, and design files and schematics for the reference carrier board for the dev kit, so you'll be able to create your own customized designs around the Nano module to your liking. Here are the other members of the Jetson family. Prior to the Nano, there was Jetson TX1, TX2, and Jetson AGX Xavier. Each has increasing compute capabilities but runs the same Jetpack software, which makes applications very portable between them, so you can easily pick the right Jetson for the right application. Nano has half a teraflop of FP16, TX1 has 1 teraflop, TX2 has 1.3 teraflops, and Xavier has up to 11 teraflops of FP16 and 32 teraops of Int8 compute. This summer, Jetson TX1 is being phased out for new designs in lieu of a 4 GB version of TX2, with the latest software support and same price as TX1, but with the performance of TX2. The original TX2 has 8 GB of RAM, but we made this lower cost 4 GB version to roll out. and there's also an industrial version of Jetson TX2, which is intended to operate in industrial environments requiring a higher degree of reliability and ruggedization. And then Jetson AGX Xavier has 16 gigabytes of memory and 32 teraops of performance, all with a common software load from Jetpack. As mentioned, Jetpacks are a distribution of software that's available to run across the Jetsons, and it's based on Ubuntu, Linux, along with NVIDIA's drivers, L4T BSP, and tools like CUDA. It's like a supercharged version of Ubuntu that comes preloaded with GPU-accelerated deep learning and computer vision libraries, along with multimedia tools for camera capture and the video codecs. You can easily install machine learning frameworks like TensorFlow, PyTorch, and Caffe on top of this, and robotics frameworks like ROS, and pretty much any programming language that has a compiler or interpreter available for Linux. There are tens of thousands of precompiled packages available for the ARM64 Ubuntu repositories to install with the click of a button or a few keystrokes from the terminal. Altogether, it forms a complete stack for creating and deploying AI-powered applications. In addition, NVIDIA's released additional SDKs called Deepstream and Isaac. Isaac's our robotics SDK and simulator, and Deepstream's for multi-stream video analytics. There are also interactive profiling and debugging tools available called Insight to help you tune the platform. The latest version of Jetpack available is Jetpack 4.2 with L4T R32.1, and it's a unified release available for Jetson Nano, Jetson TX2, and Jetson Xavier. The software versions are the same across the Jetsons, and it's based on Linux kernel 4.9 and Ubuntu 18.04 LTS. Jetpack includes full support for desktop graphics, including OpenGL 4.6, OpenGL ES, EGL, and Vulkan. Full CUDA 10 support, including cuDNN, cuBLAS, cuFFT, NVIDIA performance primitives, and TensorRT 5 are provided. For computer vision, there's OpenCV and VisionWorks, which is an implementation of Khronos OpenVX vision standard. On the multimedia side, the L4T Multimedia API provides low-level access to the codec and camera capture hardware, while NVIDIA accelerated GStreamer plugins are provided for these elements that can be used to easily chain together pipelines for remotely streaming encoded video or reading, writing video to a variety of compressed formats on disk. New to Jetpack is a new Python-based library called Jetson GPIO, which provides compatibility among hundreds of devices and peripherals that you can plug into the 40-pin GPIO header, which we'll talk more about later. Something wonderful about Jetson is that you can easily install and run the full versions of popular machine learning and deep learning frameworks on it, like TensorFlow, PyTorch, Caffe and Caffe2, MXNet, Keras, and others. Since Jetpack provides full CUDA support, including cuDNN, they are all GPU accelerated and able to get great inferencing performance running on board the device. This really streamlines migrating from your training environment to the edge device for inference. You can take your existing Python code using TensorFlow or PyTorch, for example, install those same frameworks on any Jetson, the full versions of them, and run that same code there. Really handy, and with the level of compute available from the GPU, you don't need to use reduced or limited versions of the frameworks like TF Lite for lower-end embedded processors or custom chips that only support a fixed set of network layers. These all have the ability to work with TensorRT for even better inferencing performance too. Deep learning frameworks aren't the only open source frameworks that you can run on Jetson. You can install ROS, the robot operating system, Amazon RoboMaker, and AW Greengrass for IoT. The L4T kernel also supports Docker, so you can use Docker containers, another way that people like to easily migrate their applications between the cloud and edge without extra maintenance. And for folks running multiple Jetsons in energy-efficient clusters, you can use OpenMPI for multiprocessing just like on servers. And this is just a small partial list. There are a lot of already available in Ubuntu that you can install. Most of the packages that are there on desktop are also there available for Jetson. So we mentioned NVIDIA TensorRT. It's NVIDIA's DNN inferencing accelerator library optimized for GPU. NVIDIA has cuDNN, which implements various network layers in CUDA, and TensorRT operates at the network level. With knowledge of the network graph, it's able to perform additional optimizations like kernel fusion, which evaluates multiple layers at a time within the same CUDA kernel to reduce memory bandwidth usage and latency. It'll tune itself for the platform and can fully utilize the FP16 precision available on the Nano's GPU. Typically, you'll see multiple times speed up with TensorRT, and folks will often start running with the native frameworks on Jetson, still using GPU, and then optimize using TensorRT to get the best real-time performance. How it works is you take your trained model from your framework of choice, import it into TensorRT, it'll optimize the model for the NVIDIA platform and GPU you're on, and then you can save that optimized model for next time and do the runtime inference in C++ or Python with the TensorRT API, or one of the command line tools or wrapper libraries that we've made for it. And some frameworks have integrated TensorRT directly and will allow you to handle all of this for you. Like in TensorFlow, there's a module called TFTRT, which allows you to transparently execute parts of your TensorFlow graph in TensorRT without having to leave your TensorFlow environment. This is nice if you have custom operations you've defined in TensorFlow, because TensorFlow can still run those operations and use TensorRT on the rest of the graph. TFTRT works under the covers, and you don't need to learn much of anything about TensorRT to use it. There's a second way to run TensorFlow models with TensorRT. You can freeze your TensorFlow graph to a PB file and export it to UFF format, and then load it with the TensorRT API. You don't need TensorFlow installed on your Jetson to run it like this, which some people want to avoid the overhead for production systems. Other frameworks like PyTorch support the Onyx Exchange format, which is somewhat emerged as a standard model format between frameworks, so you can export your trained model from these frameworks to Onyx, and then TensorRT has an Onyx importer that you can use to load them at runtime. It also has a Caffe importer for loading Caffe models, and for frameworks that don't support one of these formats, you can define the network directly in TensorRT and load the trained weights in that way. Next, we're going to take a look at some inferencing benchmarks run on Jetson Nano with TensorRT. Jetson Nano can run a really wide variety of network models for doing everything from image recognition to object detection, segmentation, pose recognition, and others. Here's a small selection of models trained using a bunch of different frameworks that are running on board the Nano using TensorRT. Interactive real-time frame rates are achieved on even the high-end networks up to HD resolutions. In particular, SSD MobileNet V2 is a widely used object detection network used in a lot of applications. Nano runs it at nearly 40 frames per second, and we also have a pruned version of SSD MobileNet V2 from the NVIDIA Transfer Learning Toolkit that does 70 frames per second on Nano. Pruned means that the dead weights that don't contribute to the model were removed without sacrificing accuracy. The version shown here is unpruned though, and you can easily train it in TensorFlow, and there are ports of it for PyTorch too. YOLO is another popular object detection network that we benchmark, and that's trained with DarkNet. UNet's a segmentation network that classifies each pixel in the image. Semantic segmentation is like image recognition, but instead of just classifying the overall image, like ResNet, Inception, and VGG, UNet does per pixel classification, which is really useful for perception and autonomous navigation. Another cool network is SuperResNet, which does high-quality upsampling of images called super resolution that's useful for enhancing video of noisy or low-res sensors. OpenPose is what we ran for pose recognition, which extracts the positions and orientations in 3D of human skeletal features of people in a video stream, like the locations of their arms, hands, fingers, face, feet, legs, and bodies. With this info, you can do behavior recognition and gesture recognition, for example, signaling with a robot or implementing collaborative safety features in a factory or warehouse environment. We've also compared the DNN inferencing performance with other platforms like the Raspberry Pi, Intel Neural Compute Stick V2, and the Coral Dev Board with the Edge TPU. The Neural Compute Stick and Edge TPU are chips designed specifically for inference in hardware. What we found is that these devices typically support a narrower selection of network models, often due to limitations in a specific compiler needed to compile the model for the device, or a reduced version of a framework needed, along with memory capacity and limited model resolution or layers not implemented in hardware, whereas the Nano's GPU can run practically any network from many different ML frameworks. For models that were able to be run, Jetson Nano exceeded the performance of the Neural Compute Stick V2 and was competitive with the Coral Dev Board and Edge TPU. Though Nano can handle processing multiple sensor streams and multiple networks and resolutions simultaneously, due to on-chip limitations of the hardware inferencing ASICs, these devices are typically limited to one lower resolution stream and network at a time. With Nano, you can utilize all of its multi-stream capabilities, including the codecs, camera lanes, 4 GB of memory, CPU, and GPU. Next, we're going to look at an example processing 8 HD video streams simultaneously on Jetson Nano using our intelligent video analytics SDK, Deepstream. But one more note on the benchmarks though. Although inferencing at the edge is primarily the use case for Jetson Nano, it isn't just limited to inference. Since it runs the full versions of many popular machine learning frameworks out there, you can also do transfer learning on it, where DNN models get retrained on new data. That gives you the ability to adapt these models based on data that you've collected to have it recognize new things. And you can use it for accelerating other forms of AI too, like traditional computer vision and DSP, along with lots of other applications of CUDA out there, and even by writing your own custom CUDA kernels for the GPU and software. By the way, you can view the complete data for these benchmarks on our website at the link shown here. We've included a table there with the full results for each of these platforms. Okay, now let's take a look at the Deepstream processing 8 HD streams simultaneously on Nano with deep learning. As mentioned, Deepstream is NVIDIA's SDK for edge-to-cloud intelligent video analytics, and here we're showing a video captured from Nano running 8 HD video streams simultaneously with object detection and time series analysis using Deepstream. Deepstream takes advantage of the Jetson's multi-stream video encoder and decoder hardware, along with GPIO and TensorRT to get the best performance out of the system. It's also optimized for zero copy, so there aren't any extra memory copies or transfers being made between processing steps. All this is important to achieve the max throughput of the device, which as it turns out is pretty impressive for a low-cost, low-power board. This example is processing over 500 megapixels per second across 8 1080p streams, each at 30 frames per second. A ResNet-based object detector is used for accurate tracking on each stream running at full resolution at the same time. Here we're detecting vehicles, people, and baggage and counting the number of occurrences of each type of object over time in each camera feed. Later in June, we plan to release a new version of Deepstream that fully supports Jetpack 4.2 and also server and PC, so check out our website for more info if you're interested. Since the same shared Deepstream SDK is supported on both edge devices and servers, you can use it for edge-to-cloud applications where the video is initially processed with analytics using Jetson at the edge, and then this data is aggregated and transmitted back to the cloud for further processing without needing to rewrite software or change frameworks. Here's an example architecture of a system built around the Jetson Nano module and Deepstream for handling 8 high-definition IP cameras. This is for a network video recorder box that can do deep analytics in real time, or a smart camera or IoT gateway system. The Nano module's PCIe lanes are used to connect additional network interfaces and a SATA drive for storing the compressed video on disk. You can create all kinds of custom devices and products around the Nano module, and we'll be releasing the low-level hardware docs for the module in June, along with reference schematics and design files of the dev kit carrier, so you can make your own designs like this one with it in no time. Another SDK that we mentioned earlier is NVIDIA's Isaac SDK for accelerated robotics development. It includes the Isaac runtime robot engine with algorithms and DNNs that we call GEMs for things like perception and autonomous navigation, SLAM localization and mapping, visual odometry, path planning, and stereo depth, along with the high-fidelity Isaac simulator and a suite of simulation environments called Isaac Gem, all fully optimized for GPU with CUDA and hardware graphics. You can use Isaac to train and deploy production autonomous machines and robots that require the best performance. We recently released Isaac SDK and Simulator, so you can download them now from our site and get started. Isaac also includes multiple reference robot designs like the Carter delivery robot and Kaya to get you started. These reference designs include both the software, component lists, and the plans for putting together the hardware. Here's an example pipeline of Isaac gems used by the Carter robot for navigation using a stereo depth camera and LiDAR for simultaneous localization and mapping, or SLAM. The Isaac team is hosting a webinar on May 30th, so we hope that you'll join us again then for a deep dive on Isaac. Okay, now we're going to switch gears to walk through the resources at your disposal to help you get started with the Nano, along with various peripherals and accessories available for it, and tips and tricks to using the board. There's a lot of info out there already on Jetson Nano available for you to use, like various tutorials for deep learning that we have and open source projects like the Jetbot. You can download the docs and software from our developer site, and we publish guides to the eLinux wiki too. There are lots of peripherals and accessories compatible with the Nano Dev Kit, and people have started coming out with some of the first custom carriers and enclosures for it. And if you ever need support, we have a very active community developer forum where you can ask questions and get help. Hello AI World's an easy-to-follow open source tutorial that we created to help get started deploying deep learning on Jetson. It covers inferencing with image recognition and object detection, and it comes with pre-trained networks for you to use out of the box and does live camera streaming. You can follow it in around 2 hours or less on your Nano, and during the tutorial you'll code your own image classification program from scratch. It all uses TensorRT underneath for great performance, and the core code is built into a library that you can easily use to make your own deep learning projects. Let's quickly step through the different parts of the tutorial to follow. The first thing to do is clone the repo from GitHub and build it on board your Jetson. During the build process, it will automatically download various network models and test images that you can use. Go to the URL shown here to get started reading the documentation on each step and to get the repo. Once you've compiled the code, we're going to classify some images that come with the repo, or you can download your own images to play around with. The project includes the standard GoogleNet and AlexNet models that were trained using the ILSVRC12 ImageNet dataset, which are able to recognize 1,000 different types of objects, including many different species of animals, fruits, vegetables, and different foods, natural scenes, along with man-made and household objects, vehicles, road signs, and lots of others. There's a link to the full list of the objects that can classify included in the tutorial, so you can check that list against what it's able to do. There's also a follow-on tutorial to Hello AI World where you can retrain the networks on new data to be able to classify different objects. How the classification works is there's one output neuron in the network for each of the 1,000 object classes, and each output neuron corresponds to the confidence value of that class. Then you pick the argmax, or the neuron with the highest confidence, and the index of that neuron corresponds to the object class that the network classified the image as. Okay, next we step through the code to make your own image recognition program. The C++ code shown here shows the parts relevant to loading the network, classifying the image with TensorRT, and outputting the result. This snippet is slightly abbreviated without the disk I/O, so it'll fit on this slide, but even the full version is quite simple to follow and fits in 75 lines of code, including comments and whitespace. In the future, we're also going to add support for Python to the tutorial, so you'll be able to code in Python if you prefer. Next, we're going to run the inferencing in real time on a live camera stream. You can connect a camera to your dev kit and point it at different objects around the house or little props to see how it classifies them. It's pretty fun to play around with. Remember that the pre-trained models it comes with work with the 1,000 different types of objects that they were trained on. Like all of the steps, you can dig into the code from this program and see how to stream the camera as opposed to loading the images from disk. The cameras it works with are MIPI CSI, like the Raspberry Pi Camera Module V2, or USB webcams like Logitech C920. If you're using a USB webcam, see the directions in the repo for changing it over to use USB webcams instead of MIPI CSI. The program can run up to the full rate that your camera supports in real time, so for example if you have a 30 Hz camera, it'll process at 30 frames per second. The second phase of Hello AI World focuses on object detection, which builds on the concepts of image recognition. Object detection gives you the bounding boxes and is able to classify multiple objects per frame, as opposed to the image recognition networks used in the previous steps classifying the entire image. Object detection is really useful in robotics and analytics, where you need to know where the things you're looking at are located in the frame. Like the previous examples, first we start with processing some test images from disk and detecting various objects in them. There are a handful of different models included with the repo that can detect different things like people, dogs, and various household objects. You can look at the code for this program to see how the detections performed. It's mostly the same as recognition, except that the detection network outputs a list of bounding boxes with a confidence value attached to each bounding box. Like the steps for image recognition, there's also a live camera app for object detection, which overlays the detected bounding boxes over the camera stream in real time. Here's also the list of pre-trained detection models that the repo comes with. Some users have made some pretty cool apps using their own retrained models, like this one that finds and classifies playing cards by their suite and rank. You can retrain your own models too, and that's what's covered in the next tutorial, 2 days to a demo. 2 days to a demo includes the training aspect of deep learning in addition to inferencing. Through the tutorial, you'll download some sample datasets to a host PC or cloud instance and retrain the networks used in Hello AI World with NVIDIA's Digits interactive training tool so that the models learn to recognize and detect new objects that they weren't able to before. You can then supply your own datasets to have the networks learn objects specific to your applications. It's called 2 days to a demo because you can follow it in roughly 2 days to create your own customized deep learning applications trained on your own data, which includes the time to set up your training machine or cloud instance, download the sample datasets, do the training, and test the inferencing on your Jetson. It also includes a third type of network, semantic segmentation, which is able to perform per pixel classification, which is really useful for perception and autonomous navigation where you want to understand your whole environment. The code and docs for 2 days to a demo are in the same repo as Hello AI World, and the inferencing code that runs on Jetson is the same between both of the tutorials. There are also ROS nodes provided for the deep learning networks from these tutorials, including nodes for recognition, object detection, and segmentation. They run fast since they use TensorRT like the tutorial does, and they support ROS kinetic and ROS melodic. Next, we're going to take a look at Deep Learning Robot with Nano that builds on a lot of the concepts covered in Hello AI World and the 2 days to a demo. Jetbot's an autonomous AI-powered robotics kit that we put together for Jetson Nano. It's fully open source and includes all the software and hardware docs for sourcing the components and putting it all together. The chassis is 3D printable and uses inexpensive parts, so you can build a whole kit for under $250, including the price of the Nano. Jetbot's programmed through user-friendly Jupyter IPython notebooks. These contain the deep learning functions and logic to control the bot. Out of the box, it can do obstacle detection, object following, and path following using TensorFlow and TensorRT from a low-cost monocular camera feed. You can even collect new data from your environment right in the IPython notebooks and retrain the networks on board the Nano, so it's very easy to use and create new autonomous modes for. We've also released ROS nodes supporting the Jetbot hardware, along with a gazebo simulator model for it, so if you're a ROS user, you can bring ROS components to Jetpack too. We actually have another webinar just for Jetbot coming up in 2 weeks, hosted by my teammate John Welsh, the creator of Jetbot, so we hope you'll join us again next time for that. Let's watch a short video from John about what Jetbot can do.
So over here we have Jetbot, which is an open source robot that we built using Jetson Nano. And the idea behind Jetbot was to give people that wanted to start with AI or maybe AI with Jetson Nano a platform that they could just get up and running right away. You buy the components of the robot. We have everything on GitHub, so it's super easy to get started. It's all done in Jupyter notebooks. So we have like basic examples from just controlling from your web browser in Python. It's super easy to do. To more complicated examples like using AI for avoiding collisions. And then we go all the way to road following to have like kind of an autonomous car navigating a Lego city. So that's the basic idea, is that you can start with this platform. It's all open source, the hardware, the software, and then you can take what you learned, you can take the components even, and you could build something new, and who knows what that would be. It would be kind of up to you.
Okay, next let's walk through setting up a new Nano dev kit out of the box. The dev kit boots from a micro SD card, so all you need to do is download the SD card image from our website, which already includes all of the Jetpack components, and flash the image to your micro SD card from any PC that has an SD card slot. You can easily flash it with a common tool called Etcher that runs on Windows, Mac, or Linux, and there are a number of other tools out there that can do it for you as well. The directions for flashing are included in the link at the bottom here. When you're done flashing, you take the formatted SD card out of your PC and insert it into the slot on your dev kit. The microSD card slot is located on the underside of your Nano module on the side opposite facing the connectors. It's recommended that you use at least a 16 GB UHS-1 microSD card. The faster the class of the SD card, the faster it will boot up and load. And you can use as large a microSD card as you want. There isn't a limit on the storage capacity, and your user partition will automatically be expanded to fill the entire SD card. So that gives you extra space to store data and install lots of packages. There's also a second way to flash your Nano, and it's similar to how the previous Jetsons were flashed with Jetpack. First, you insert your blank microSD card into the dev kit, connect its micro USB and Ethernet port to the Linux host PC running Ubuntu, then enter it into recovery mode using the J40 button header. Then you use the NVIDIA SDK Manager application running on your host PC to flash the OS and install the Jetpack components. The NVIDIA SDK Manager allows you to select exactly which Jetpack components you wish to have installed, and it's how the production Nano modules that use eMMC will be flashed because they don't have SD cards. But if you're using the dev kit, it's generally easier just to use the primary method of flashing the bundled SD card image with Etcher, because you can use that from any PC running Windows, Mac, or Linux that has an SD card slot for doing that. When you're all flashed and have inserted the micro SD card, connect a keyboard, mouse, display, and power supply to your dev kit, and the board will automatically turn on and start booting up when you plug it in. You should see a green LED light on the carrier board when it turns on. The first time you boot up with a new SD card image, you'll need to go through some basic setup steps with Ubuntu, like entering your desired username and password and setting the time zone, similar to what you would see setting up Ubuntu on a PC system actually. For this initial configuration, you'll need to have a monitor, keyboard, and mouse connected, but after that you can operate it headless if you want. And in the next version of Jetpack, we're adding support for headless setup, so you won't need a keyboard, mouse, or monitor at all if you don't want. There are multiple ways that you can power the dev kit, which makes it quite versatile to use in projects. You can use a micro USB adapter capable of delivering at least 2 amps of power. If you've connected a bunch of peripherals to the board, like USB devices or unpowered USB hubs, and are running a demanding computational load, then you may want to step up to using the DC barrel jack with a 5-volt 4-amp power supply. If you want to use the DC barrel jack, remember to fit a standard 2.54mm jumper on the J48 power select header. This switches the board between accepting power from the micro USB port to the barrel jack. In this mode, you can also connect a power source to pins 2 and 4 on the J41 expansion header, 3 amps per pin or up to 6 amps total. Pins 2 and 4 should be 5-volt DC, and pin 6 should be connected to ground. It's important to use a high-quality power supply with the Nano that's capable of delivering a consistent 5 volts that won't dip to under 4.75 volts under load. Many typical USB phone chargers aren't designed to deliver this kind of consistent power source, as that isn't what your cell phone really needs, and also these cables that they use can have additional voltage droop. The board may boot up with some of these chargers, but when you plug in more peripherals or go to run something more demanding, the board may brown out and shut off. So we have some power supplies that we've verified here and also in our supported component list document that you can download from the developer site. Highly recommend that you pick one of these up to go along with your dev kit. And of course, you can also power the Nano from a battery pack via the micro USB port, DC barrel jack, or J41 expansion header. Like some of these portable USB battery packs that put out 2 amps seem to work pretty well. If you're using a LiPo or NIM battery, you'll probably need to use a voltage regulator to get it at a consistent 5 volts. Now there's actually a fourth way to power the board, and that's the power over Ethernet. The Nano's Ethernet port is enabled with PoE, but power over Ethernet typically supplies 48 volt DC and the Nano needs 5 volts. So if you want to use PoE to power the board, you'll need to use a PoE hat or a step-down voltage regulator to convert it from 48 volts down to 5 volts. The 48 volt source is automatically routed from the Ethernet port to the pins on the J38 PoE header. Either attach the PoE hat to that, like the Raspberry Pi has a PoE hat which fits the Nano that has the regulator on board and will take the 48 volt source from J38 and connect the step-down 5-volt power to pins 2 and 4 on the J41 expansion header for you. Or you can manually wire a regulator of your choice between J38 and J41. I mentioned on the last slide that the board will automatically turn on and start booting up once power is applied. You can change that behavior by fitting a jumper to pins 7 and 8 on the J40 button header, which will disable auto power on, and then you'll need to short pins 1 and 2 on J40 to power it up. In addition to the power on signals, J40 also has pins for resetting the board and entering it into recovery mode. You can connect momentary push buttons to J40, which are really convenient to press, or you can just use jumpers on them when you need to. An extension of the discussion on power supplies is the power modes that the board's able to run in. Nano has 5 and 10 watt power modes, and by default it'll boot up in 10 watt mode, which gives you the best performance. If your power supply is acting up on you, you can try putting the board in 5 watt mode so it draws less power until you can get a new one. NVP model is the software tool used to change power modes and tweak profiles depending on your use case and your application's TDP. You run the NVP model-Q command to query the current mode, NVP model-M to change modes. When you change modes, the new mode will persist after reboot, so you don't have to worry about making a startup script that sets your desired mode. You can also define your own custom power modes too. They're located in the etc/nvpmodel.conf file, and they look like the configuration shown here listing the various clock frequencies. What NVP model does is it sets the minimum and maximum voltage limits and clock limits of the CPU, GPU, and memory that are used by the dynamic voltage and frequency scaling governor, also known as DVFS, and the number of CPU cores that are online. The DVFS governor will scale depending on workload depending on these frequencies defined by the active mode. Now, if you want to disable DVF scaling, the Jetson clock script will disable DVS and lock the clocks to their maximums for the active power mode. Jetson clocks doesn't change the active mode, it just maximizes the clocks to their limits for the current mode. NVP model and Jetson clocks are command line tools, but in the next Jetpack release, you'll see a little NVIDIA icon appear in the status bar, and this will let you configure and monitor the power settings of the system through the GUI. Now, to keep an eye on system performance, you typically use a program like Top or the Ubuntu System Monitor. However, there's a lot more information available for Nano, so we have a tool called TensorRT, which displays all of the stats that you wouldn't get otherwise, like the utilization and frequencies of the GPU and memory controller, temperatures from the thermal sensors, and power measurements from the onboard INA sensors. The INA sensors measure the power consumption across different power rails, including the usage from the CPU and GPU, and the overall power usage of the board. There's a section on TensorRT included in the L4T developer guide at the URL at the bottom here, and it documents all of the different settings and outputs that the tool produces. Recommend that you try running this in the background while you're benchmarking or profiling your application, so you can keep an eye on the core utilization, memory bandwidth and consumption, and the different clock frequencies as they change dynamically at runtime with the DFS governor. The Nano Dev Kit has a 40-pin expansion header, J41, similar to what's found on the Raspberry Pi, and is compatible with many of the same peripherals and hats. It's supported in Adafruit's Blinka Python library and Seed Studio's Grove library, which all told support over 400 devices and sensors that you can use. By default, the Nano's 40-pin header is configured to expose 2 SPI ports, 2 I2Cs, UART, audio, GPIOs, 3.3 volt and 5 volt power pins. The protocol interfaces like SPI, I2C, I2S, and UART are referred to as special function units or SFIOs. Using the pin muxing tool, you can reconfigure the Nano's device tree to change these SFIO pins over to GPIO. To access the GPIO pins directly, there are a few APIs you can use from user space for doing this. Jetpack now ships with the Jetson GPIO library for Python, which provides the same interface as the RPi GPIO library, so existing code and drivers using RPi GPIO automatically can use the GPIO on Nano too. You can find the library, documentation, and samples located in the opt NVIDIA Jetson-GPIO directory. For using GPIO from other programming languages than shell scripts or from the command line, the GPIO pins are exposed in sysfs under the sys class GPIO folder, which is the standard location for these in Linux. To use them, first you have to map the particular GPIO pin you want into user space by writing the sysfs pin number to the export file with sudo permissions. This will let the Linux kernel assign ownership of the pin over to the user space driver. You can see the sysfs pin numbers here to reference in the diagram. For example, on this slide we are working with GPIO number 38, which corresponds to the GPIO PE6 signal or physical pin number 33 on the J41 header. After exporting the sysfs pin number, a directory for the pin will be created, in this case the GPIO 38 directory. Inside that directory there are a bunch of files that control the pin and read and write to it. First, set the direction that you want for the pin by either writing in or out of the direction file. In this example we're using output, and next we set the pin to be either high or low by writing to the value file. A value of 1 is high and 0 is low. After setting it high, if you connected a multimeter to the pin, you would see it reading 3.3 volts, which is the logic level that the Nano expansion header uses. Now if you wanted to input and read the value instead of output, first you would set the direction to in, and then you would read the current value of the value file with cat or the file IO APIs from any programming language like fopen or fread in C or C++. Actually, the Jetson GPIO library uses the files underneath too. You can check out the Linux documentation for the sysfs GPIO interfaces at the link here. It goes through other features like receiving interrupts as well. When you're done using a pin, unexport it, and that pin's directory will be unmapped and freed up. And if you want to instantly check the status of high-low values of all the GPIO pins in the system, you can cat the syskernel-debug GPIO file, which will print them all out for you. The special function units typically have their own software interfaces. In the case of I2C, there's a cross-language API called libi2c for C++, and Python that you can install from the Ubuntu apt repo. As mentioned, there are hundreds of compatible devices and hats that you can plug into the 40-pin expansion header. However, there are lots of other accessories that have already been created for Nano, including a number of 3D printable enclosures for the device, aftermarket carrier boards with additional I/O, and sensors like CSI imagers and stereo cameras. You can find links to these on the eLinux wiki or from our ecosystem partners, and we anticipate a lot more becoming available this year. The camera header on the Nano dev kit is compatible with the Raspberry Pi Camera V2, and drivers for the IMX219 sensor that it uses are included in Jetpack, so it works out of the box. And Leopard Imaging and Econ systems also have MIPI CSI cameras available that work too on the Nano. Since Jetson's frequently used to process live camera streams, let's talk about how to capture video from software. NVIDIA has an optimized library called Argus, which is part of the L4T multimedia API, which provides image acquisition for MIPI CSI sensors. MIPI cameras have the benefit of being chip-to-chip and being ingested directly into the Jetson hardware without needing to go through the CPU or have extra memory copies. Argus is optimized for zero-copy and low-latency multi-camera applications. With Nano, you can stream up to 3 4-lane MIPI CSI2 cameras or up to 4 MIPI cameras in 4-lane 2-lane configurations. Overall, there are 12 CSI lanes for you to use on the module. Argus has APIs for C++, and there's a wrapper library which includes support for Python that you can find on our GitHub. We also support GStreamer and Jetpack, and we provide a number of hardware-accelerated elements to use in GStreamer pipelines for accessing features like the camera interface and video codecs. Here's an example pipeline that you can launch from the command line that uses our NV-Argus camera source GStreamer element, which does camera capture with libargus. With GStreamer, you can patch together a lot of different pipelines for compressing the video and recording to disk, or compressing and streaming out to a remote host via RTP or RTSP, and lots of different things. There's also a test camera viewer called NVGST Capture, including with Jetpack, that's good to use once you plug in your MIPI camera to verify that it's working okay. A standard video API for Linux is called Video for Linux 2, or V4L2. V4L2 cameras get mapped to a device node under Dev Video, and on Jetson MIPI cameras, they'll show up under there. V4L2 also supports USB webcams and various other camera protocols, and you can use it by either accessing a Dev Video device, using file I/O from any language, or by using a wrapper library like those mentioned here for C, C++, and Python. There's also a GStreamer element for V4L2 capture called V4L2 Source, so it's easy to swap that out for USB webcams in your GStreamer pipelines. Another important part of Jetson's multimedia capabilities are its multi-stream hardware video encoder and decoder engines. Nano can decode up to 8 1080p 30 H.264, H.265 streams and encode up to 4 1080p 30 streams simultaneously. It can also decode two 4K P30s and encode a 4K stream simultaneously, and in addition to H.264, H.265 compression, it supports VP8 and JPEG profiles for encode, and VP8, VP9, VC1, MPEG-2, and JPEG profiles for decode. At runtime, you can mix and match the profiles, number of streams, resolutions, and frame rates shown in the tables here up to the aggregate bandwidth of the encoder and decoder. The encoder and decoder are independent hardware units, so they can be utilized to their fullest at the same time without impacting performance. To use these codecs from software, there are a couple APIs for them that NVIDIA provides through Jetpack. First, there are accelerated GStreamer elements available for each of the profiles that do encoding and decoding, for example, OMX H.264 and OMX H.265. Here are some example GStreamer pipelines that encode a H.265 video to disk in MKV format, and then a second pipeline that decodes the MKV file and decompresses it from H.265. You can also easily connect the camera elements from the previous slide to the encoder and record or stream out your camera video. There are lots more example GStreamer elements and pipelines included in our L4T Accelerator GStreamer user guide that you can download from our developer site. To see all the GStreamer elements available on your system, you can list them with the GST and spec command. There's also a hardware video image conversion and compositor engine available, exposed in GStreamer through the NVVidComp element for doing color space conversion, cropping, rescaling, rotation, and temporal noise reduction in hardware. The second set of APIs that NVIDIA ships for the codecs are V4L2 extensions from Jetpack's L4T multimedia API that support H.264 and H.265. V4L2 actually defines interfaces for more than just camera and video capture, so we provided extensions to these for doing hardware encoding and decoding through V4L2. The devices show up as dev NV host nodes, and there are examples and documentation including with the multimedia API that show how to use them. The V4L2 encoder expects the data to be in YUV format and outputs the compressed bit stream, whereas the V4L2 decoder accepts the compressed bit stream and outputs the decompressed frame in NV12 or YUV format. V4L2 is lower level than GStreamer, so the file I/O and depacketing needs to be performed. The hardware video conversion and composter is also available through V4L2 as the dev NVHost-VIC node. One final topic we're going to cover today is Jetson's unified memory subsystem and zero copy. All of the processor cores in Jetson's share the same common memory controller and physical DRAM, including the CPU, GPU, camera ISPs, codecs, multimedia engines, and high bandwidth I/O controllers. That means you don't need to have extra memory copies between the different cores. They can simply reference the same memory used in the previous processing step in the pipeline. Eliminating these extra memory transfers is called zero copy, and it greatly reduces latency and the amount of memory bandwidth wasted, freeing up that bandwidth for other purposes. Ultimately enables you to process more streams at the same time, which coupled with the optimized inferencing in TensorRT is one reason why Nano is able to handle up to 8 HD streams simultaneously. When you're working on the GPU, you may be familiar with the CUDA memcopy function, which is used to transfer data between the CPU and GPU. On typical PC systems, the GPU is connected over PCI Express, and it has its own discrete memory, so it doesn't share memory with the CPU and needs to shuttle around data sometimes. However, on Jetson, you don't need to use CUDA memcopy because all the memory in the system is shared, and you can just map the same pointer into the GPU's address space. There's a couple APIs in CUDA for accomplishing zero copy, and you can use map memory with CUDA host alloc and CUDA host get device pointer, or you can use CUDA's more recent unified memory feature with the CUDA malloc managed API, which is also able to implicitly handle synchronization. Consult the CUDA documentation to determine which approach is more beneficial for you. Other engines can use zero copy in addition to the GPU, like the camera ISP and codecs with EGL streams, which are interoperable with OpenGL and CUDA. So you can do zero copy between more than just the CPU and GPU, practically the whole system. It's highly recommended to take advantage of these techniques when optimizing your applications to achieve the peak performance and utilization from the device. Okay, so that brings us to the end of today's presentation. Thanks again for watching, and we hope you'll tune in to our next webinar on Jetbot and join us creating fun gadgets and AI-powered gizmos with Nano. We've covered a lot of material today, and you can download the PDF of these slides for your reference from the webinar viewer, and they'll also be posted to GitHub and the Jetson forums. All of the links are clickable in the PDF, by the way. If you haven't already, check out our technical blog, Jetson Nano Brings AI Computing to Everyone. It includes more details about Nano and a full table of the benchmarking data that we talked about earlier. Okay, now we're going to get set up for Q&A, so if you have any questions, enter them into the webinar chat now. We'll stick around for as long as we can, but if we don't get to your question, please feel free to post it to the forums and we'll get back to you soon.
Okay, everyone. Thanks again for joining us today. We're going to answer a bunch of questions now. So if you haven't already, please type in your questions if you have them into the webinar chat. Let's start with a question on which power over Ethernet hat would you recommend to use with Jetson Nano, and can the Raspberry Pi PoE hat be used? And yes, that is the one that we tested with. The Raspberry Pi PoE hat. I think it might be one of the only ones that is, meant to fully integrate that all together. So that would be the one to try. Otherwise, you can easily, wire any voltage regulator to do PoE if you want. Here's a question: does Nano support any deep reinforcement learning library? And so the answer is that there's a lot of deep reinforcement learning code out there in TensorFlow or PyTorch that you can run that you can use to do reinforcement learning on the Nano, typically used for robotics and stuff like that. Is it possible to support 4K P60 encode on the Nano? I believe it only supports 4K P30 encode, but it does do 4K P60 decode. Okay, next question. Is there any TensorRT Python API available for Jetson Nano? And since Jetpack 4.2 came out, which was the most recent release, the Jetson Nano, Jetson TX2, and Jetson AGX Xavier all support the TensorRT Python API. And as mentioned, we'll also be adding support for Python into the 2 days to a demo and Hello AI World tutorials, so you'll just be able to do them there. How many gigaflops does Jetson Nano have available? The answer is 472 gigaflops of FP16 from the GPIO. Here's a question about zero copy. Does zero copy mean that I don't need to do memory transfers between the CPU and GPU like on a PC system? And that's exactly what it means. You don't need to unnecessarily transfer memory between the two because it's all the same memory on the Jetson, whereas on PC systems, typically the NVIDIA GPU is like a separate PCI Express board that has its own memory. So on Jetson, it's all the same memory, and therefore you can just pass the pointer around, essentially. I see some questions here about is the Nano available for purchase, and what's the availability of the Nano boards? The boards are available worldwide currently. We are increasing the supply of those over the coming weeks. So if you have trouble getting one currently, encourage you to sign up for our lists, and we'll email you as soon as more available. And there are a lot of distributors that have them in stock if NVIDIA.com's out of stock. And you can see the list of distributors in this slide there, like Amazon, Newegg, Seed Studio, and SparkFun, Arrow, and others. So if the NVIDIA.com web store is out of stock, please check with those other guys because they typically have stock as well. Let's go to a next question here. There was a question about if I'm a TX1 user, what should we expect for Jetpack updates for TX1? And the answer to that is that we recommend TX1 users, if you're not moving to Jetson Nano, that you move to the Jetson TX2 4GB version that's coming out, because the TX2 4GB has the same amount of memory as the TX1 and the same price as TX1, but it has the compute performance of TX2 and the software support of TX2. So for any new designs that are going forward with TX1, I recommend that you either use Jetson Nano or this new TX2 4GB version for that. Here's a question about, can you tell us when the design files for the Jetson Nano hardware and the other design collateral will be published? That'll be published later in June, along with the production release of the Jetson module. And that will include all of the design files that are typically seen with the previous Jetson. So there'll be, hundreds of pages of docs for all the pinout and module data sheet and all the design files and schematics and collateral for the carrier board that comes with the dev kit, just like the previous Jetson. And the reason they weren't already released is we're making a few minor updates to the production module before we release it. That won't impact performance or usability. It's just more of an internal thing to, for qualifications and production use and such. And we just want to make sure that all of those docs are aligned together. So it does look like we reached the top of the hour. We're going to stick around and answer questions for a while longer. But if you have to drop off now to run to another meeting or whatnot, no worries. The recording of this webinar will be available later this afternoon. And if we don't get to your question, sorry about that. You can post it to the forum anytime. You'll find us there as well. But we'll stick around and answer a bunch more questions now. Here's a question. Do I have to use one of the USB ports to add Wi-Fi? So if you want to add wireless adapter to your Jetson, there's two predominant methods. One is with a USB dongle. A second would be to use the M.2 key E port, which is a little mezzanine that it's actually underneath the Nano module on the dev kit. So you take the Nano module off, put a little M.2 key E on there. The advantage of the key E M.2 is that it supports PCI Express. So typically with these higher end AC high bandwidth Wi-Fi adapters, those might benefit from the usage of the PCI Express, or you can use the USB port. And we have supported Wi-Fi dongles and M.2 modules in the supported components list that you can download from the website. So you can see ones and those ones already have the drivers pre-installed. And that doesn't mean other ones you can use as well. You might just have to compile the kernel module driver to support that, or install the firmware for it that Wi-Fi modules typically have. But the ones in the supported components list already have the drivers and the Wi-Fi pre-installed on the SD card image that it comes with. Here's a question about, does Jupyter Notebooks run on the Nano or on the development laptop? For example, the Jetbot is all based around these Jupyter Notebooks. And the answer is that they can do both. You can, run them on your laptop. You can run the Jupyter server on your laptop and just connect your web browser on the Nano if you want. But the Nano is very capable of running the Jupyter server on board the Nano, which means that all of the commands that get executed inside those Jupyter IPython notebooks that are doing TensorFlow or whatever, those get run on the Nano too. So typically, yes, you just run the Jupyter server on the Nano itself. Okay. Do I need a separate NVIDIA-enabled PC to develop for the Nano? And the answer is the Nano is the first Jetson that does not need really a whole separate PC for the whole flashing procedure. You do need some other type of PC to take an SD card and write the image to it, but it can be any laptop or desktop that runs Windows, Mac, or Linux and has an SD card reader on it. Previously, you needed a Linux Ubuntu 16.04 or 18.04 machine to flash Jetpack to your Jetson TX1, TX2, or Xavier. With the Nano, all you need to do is write the SD card image from any PC, really, and then just pop that SD card into the dev kit, which is really the reason we went with the SD card for the Nano, because it really makes that whole startup procedure much simpler. And in the production module, that uses onboard eMMC storage, because in like a production embedded system that needs to be more ruggedized out in the field, you don't necessarily want an SD card bouncing around. And that you would use the NVIDIA SDK manager from an Ubuntu machine to flash. But the dev kit can be set up from any host PC. Okay. The next question, there's a question about ROS2 support. And we have been in communication with the ROS user group about ROS2 development. I haven't personally tried ROS2 yet, but I know we're plugged in to the consortium, so I think it would absolutely be supported. I just haven't tested it myself yet, but I know that ROS Melodic is thoroughly tested, and there's been a lot of people using that so far. Here's a question about, so the Nano boots up into 10-watt mode as default. The MVP model is 10-watt mode. How long does it take to configure the device to 5 watts? And it's just one simple command line. It's sudo nvp model -m1, and that's it. It changes it to 5 watts, and instantly it's changed to 5-watt mode. So it can be done fairly instantly. And if you're talking about more of like a real-time, like how quickly can I scale, you can make your own NVP models that set the clock ranges and then allow the DVFS governor to scale between them. Or if you look at the source of the Jetson clock script, that will show you how to set your own clock rates defined within the ranges of the MVP model at runtime through the sysfs files. So you can do that at whatever frequency you want. Here's a question, is TensorFlow installed in the OS image? TensorFlow is not included with the OS image itself when it boots up, but we do have links to precompiled pip wheel installers for TensorFlow and PyTorch actually on the forums and our developer website. So, to prevent the SD card image from being larger than it already is, we try to keep, lots of frameworks out there, and also because the frameworks tend to upgrade versions quicker. So you can very easily download the TensorFlow installer right from the forum, which we update with new builds pretty frequently, especially with the PyTorch ones. So you can install those right from the commands there. What stereo vision cameras do you recommend for depth perception? So the Stereolabs explicitly supports Jetsons and the Jetson Nano. They have the Stereolab Z, which is a 2K stereo camera. They also have this nice little Z Mini. So we highly recommend those because they come with support for CUDA software. Econ Systems also has a very good stereo camera. Actually, they have a couple stereo cameras. One's a USB 3, and they also have a MIPI CSI stereo camera that work well. And then there's also a vendor, Duo 3D. They have stereo cameras that support CUDA as well. So the main part is to find stereo cameras that support CUDA for doing all of the stereo disparity mapping and such, because you don't want that done on the CPU. Okay. Here's a question, does Nano support RTSP video cameras? The answer is yes, through GStreamer. That has support for RTP and RTSP in it. When GStreamer is really great because it has like hundreds of different elements, and if you install different plugin packages, it has thousands of different elements that it can do different camera formats and different video codecs with. And streaming RTP and RTSP is one of those. So you can both stream the videos in and stream them out remotely and use the hardware video codecs to transcode and decode and encode those out, which makes it really convenient if it's attached as an edge device. Can you do 8-bit integer inference on Jetson Nano? So Nano does 16-bit floating point inference and 32-bit floating point. It does not support 8-bit inference like the Jetson AGX Xavier does. Is there a low-cost LiDAR you can recommend to plug into Nano? I personally use the SlamTech RP LiDARs. They seem to be, pretty affordable and have quite good for performance for the price point. And there's also a lot of people I know that use like the Hakoyos, and in general, LiDAR prices seem to be coming down, so that's very nice. But I've used the SlamTech RP LiDARs with Jetson for years now. Okay, so what MIPI cameras do you recommend for Jetson Nano, and what's the min-max resolution of those? So we have a list of the MIPI cameras that have already been verified to be supported on the eLinux wiki, so I recommend that you check those out. The ones that the drivers automatically come pre-built into the SD card image with are based on the IMX219. Like the Raspberry Pi camera and some other cameras that are based on that sensor. But other imaging partners like Econ Systems and some other vendors like Leopard Imaging also have cameras, and they provide the drivers for those. And on the high end of the resolution, you can do 4K P60 MIPI CSI cameras with Jetson Nano. Those 4K P60 cameras generally use 4 CSI lanes or CSI X4, and if you recall, you can connect up to 3 of those 4-lane cameras simultaneously. So you can stream 3 4K P60 MIPI CSI cameras at once. Okay, let's go on to the next question. Here's a question about the Isaac SDK. Where can I get the Kaya and Carter robot kit? Those are included in the Isaac documentation that's right on the website. So if you just Google NVIDIA Isaac SDK and then go to the docs, you can buy all the components for those and build them yourself. The Link one, I think, is still to be released. That one has a multi-Xavier, but that'll be like all the other reference ones. So the Kaya one is based on a little 3D printed chassis, and the Carter one is based on a Segway platform. Kaya is using the Nano, and Carter uses the Xavier. How is it possible to connect more than one camera because it only has one Ethernet port? Well, it turns out there's lots of different camera interfaces that you could use on the Nano. You have USB 3 streaming, you have the gigabit Ethernet, and the dedicated interfaces are the MIPI CSI that we just mentioned. And MIPI CSI has the advantage of being a direct camera interface with hardware offloaded ingest and camera capture. So unlike Ethernet IP cameras where you need to use the CPU for the depacketization and handling the IP stream, same kind of thing with USB. You need to use the CPU to run the USB driver. The MIPI cameras are completely hardware offloaded. And as mentioned, you can connect 4 MIPI CSI cameras simultaneously in X2 or X4 lane configurations. And there's 4 USB 3 ports and there's an Ethernet port. So you can connect a lot of cameras simultaneously if you use multiple interfaces for them. Could you provide the details of when the Deepstream demo is going to be available for Nano? So it's planned to be later in June, along with the next Jetpack release of when that Deepstream will be available for Jetson Nano. So stay tuned for that. You can also sign up for updates about Deepstream release on our Deepstream website or post to the forum about it. Here's a question, is the Gazebo simulator supported? Yes, it does run Gazebo. The version of Gazebo that comes with Ubuntu 18.04 is Gazebo 9. So you can easily run that and just install it right from the command line. And for those of you who aren't familiar, Gazebo is the simulator typically used with ROS. And we have a Gazebo simulation model available for the Jetbot that you can use. Here's a question about how do I clone the SD card image of my Nano, or how do I customize the SD card image? So since it's just a removable SD card, it's pretty easy. First, you set up your SD card with the stock image from our website. You plug it into your Nano, you do all your customizations and tweaks and install all your packages and code and stuff on the Nano. Then when you have your installation where you want it to be, you pop out the SD card out of your Nano and put it back into the PC that you used to initially flash the SD card. From that PC, you can run tools that can save the SD card image. There's tools like this for Windows, Mac, or Linux available. It's basically the opposite of the Etcher tool, which writes an SD card image. You want a tool that reads the SD card image to a file on your PC. Then once you've done that, you can write that SD card image back to other SD cards that you can then plug into other Nanos with your customized image. Okay, we're almost out of time here. Got to run soon, but let me answer a few more questions for you here. And, as mentioned, if we don't get to them, please just post to the forum. We tend to answer a lot of the questions, either us or the community there. Is there any GigE Vision camera support? Through GStreamer, I think there's a couple different libraries that you can install that do GigE Vision in Linux and different plugins for that. So if you look around, you can find different interfaces for GigE Vision cameras. Or some actually GigE Vision vendors have AR64 builds available. Because typically with GigE Vision, the camera vendors themselves have an SDK. Point Grey comes to mind. They actually make AR64. AR64 is the architecture of these ARM 64-bit boards. So like x86 has a different build architecture than AR64. So if you have a closed source SDK, like a lot of these GigE Vision SDKs are, you need to ask them to either provide it or download it from their website, like Point Grey has one. Or, there are some open source Linux projects out there that do support GigE Vision that you can just compile, and some of them even have GStreamer plugins too. Okay, we'll do one more question here. How many displays can you connect simultaneously to the Nano? And the answer is that to the Nano Dev Kit, you can do 2 displays simultaneously. You can do HDMI and DisplayPort, or there have been people on the forum that reported they've used a number of different adapters to, adapt DisplayPort to HDMI or even to VGA. So you can fully utilize Jetson Nano as a multiple display system, and it supports full OpenGL on both of those displays. So it's been really great joining you guys, and thank you for all of the great questions. And for those of them we didn't get to, sorry about that, but you can find us right there on the forum, and my colleague Lon just sent out a link to that right here at the top. And the slides, you can download, and those also have links to the forum and the other resource we talked here. So thanks again for joining us, and have a great rest of your day.
Thanks, Dusty, and thank you everyone for joining us. As Dusty said, there were tons of questions that were submitted that we just weren't able to get to, so please post those on the forum. We have recorded this presentation along with the live Q&A, and we will have that along with the slides available shortly for you guys on demand. You'll receive an email from us later on this afternoon with a link to the slides as well as the replay. And then don't forget to register for our Jetbot webinar coming up on May 16th, as well as our Isaac SDK webinar on May 30th. And as always, it's always great to become an NVIDIA registered developer, so you have access to the latest news on products, software, events, and of course our awesome webinar series with Dustin and the rest of the crew. So thanks again for joining us, and have a great day.